If you're watching this video, you've been told that you're going to have to learn a little something about atomic theory. And if you're like me, your first thought was, oh man. Well, fortunately for you, I'm going to try to make this as interesting as I possibly can. And when you're done, you should be an atomic theory superstar. First, you need to know about the history of the atom because the current model is super complicated to understand. And I don't want to hit you over the head with this amazingly complicated, hard to understand model. So what I'm going to do is carefully, gradually, slowly take you through some of the highlights of the important people and how they arrived at some of their ideas that eventually got us to where we are today. And then maybe a little later, you'll start to have some ideas about quantum mechanics that even the really smart dudes had a problem with. Now, while there's some dispute about who actually did this, this is Democritus, and he's the dude who's given credit for this, but his teacher, and I might slaughter his name, so I'm not going to say it, but Leucippus is how I think you say it. Anyway, he's the one they think may have done it, but, you know, hey, life's not fair. The student got the credit. Anyway, Democritus, way back a really long time ago in the land named Greece, there were a bunch of people called Greeks, and they thought about everything, including the nature of matter. Well, they came up with this idea, Democritus or his teacher, it doesn't matter, that atoms were indestructible, itty-bitty, tiny little particles that made up everything. And by packing together in different ways, they could make different materials. However, at the time of Democritus, see, he wasn't the big head honcho at the time. That was this guy, Aristotle. And everybody thought that the idea that an atom made up everything was ludicrous. And they're like, dude, you are so out of whack. See, because Aristotle said the universe is made up of 4 things. And the only 4 elements in the universe are fire, water, air, and earth. That's all. And your whole atomos indestructible idea, that's just stupid. So nobody listened to Democritus because he wasn't this awesome guy, Aristotle. Even though we now know today that that awesome guy was just flat wrong. At the moment, I am skipping some really cool people like Lavoisier and going straight to this guy because for our purposes, this is just sort of a gloss over thing. Well, atomic theory. This guy, John Dalton, over the first bunch of years of the 19th century, he came up with an explanation that he believed explained everything you needed to know about atoms. As it turns out, he was wrong, but at the time it was the 19th century, and people back then, well, they just didn't know any better. And in all honesty, most of what he said really was true. Well, here's the first thing he said. All matter is composed of atoms, which are small and indivisible. Well, they are divisible, but he didn't know that then. But everything is made of atoms. That part, he got that. All matter is made up of tiny little particles called atoms. And we visualize those as being little tiny balls. And he said that all atoms of a given element are alike, but are different from atoms of every other element. So what this means is one atom of one type looks one way and an atom of another type looks another way. And this is a pretty good approximation as all atoms of the same element have the same number of protons. However, all elements have different forms of atoms referred to as isotopes, which I will cover later. And it does have a different effect on the properties, but it does keep the atoms from being identical. So this part was false. But again, like I said, it was the 19th century and Dalton didn't know any better. He said compounds are formed when atoms are combined in fixed proportions. So what that basically means is if you have sucrose or glucose, those chemical formulas are always going to be the same. Or like water. Water's H2O. It's always going to be H2O. He said a chemical reaction involves the rearrangement of the atoms, and the atoms themselves don't change, which, considering he said atoms were indestructible, indivisible, couldn't divide it, that makes sense that in a chemical reaction, the atoms themselves don't change. These are some of Dalton's original drawings modified for digital viewing. And if we use A's and B's, we can see that when A and B get together, they're still A and B. Again, chemical reactions. The atoms do not change. They just get rearranged. Once again, we're going to fast forward a little bit to this guy, J.J. Thomson. And what this guy did was he got a Nobel Peace Prize for his work on finding the electron. Anyway, apparently Thomson had all these little cathode tubes just sort of sitting around, and he decided to hook them up to a battery. And when he did that, he got a beam of light passing from one end of these basically vacuum chambered, absolutely no atoms inside tubes. And apparently, you know, he also had a lot of time on his hand because he's like, wonder what the dealio is with this light. After all, if there's nothing in the tube to start with, where'd the light come from? He figured it must be coming from those electrodes. Since, you know, the electrodes are made of atoms, all atoms, well, then the atoms somehow must be coming apart. So he's like, well, what if I took this magnet? Or better yet, how about an electric field? What if I took this electric field, a positive and a negatively charged plate, and I put it towards this beam? Well, you know what? He found out that the beam bent towards the positive side of the magnet and away from the negative side. Well, because we know that like charges attract and opposite charges repel, he concluded that the beam coming off those metal plates meant that the atom was not only coming apart, but was coming apart with things that are negative coming off of the electron.
A cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the two metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes this specially coated surface, the cathode ray produces a strong fluorescence or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction. In 1897, J.J. Thomson, an English physicist, determined the charge-to-mass ratio of an electron. He adjusted the electric field so that the electrostatic deflection, theta E, was the same as the magnetic deflection, theta B, and was able to calculate the charge-to-mass ratio of an electron using the following equation, where E is the applied electric field, theta is the angle of deflection, B is the applied magnetic field, and L is the distance traveled by the cathode rays. Thomson determined the charge-to-mass ratio of an electron to be negative 1.76 times 10 to the 8th coulombs per gram.
Well, this led directly to his plum pudding model of the atom, which apparently is named after dessert that nobody can eat without throwing up. This model represents two very important parts. The first part of his model says, okay, see these little like plummy raisin looking things? Those are the negatively charged particles that we're going to call electrons. And all of this doughy stuff through here, that is the positive charge, because, you know, we knew at that time that atoms were neutral. So if an atom is neutral, has no charge, And we can see clearly from his cathode ray tube experiment that negative particles were coming off of the atom. That means the atom has to have an equivalent positive charge. Now, he didn't know the name of it, so I'm not going to write it. But he said, hey, if part of the atom's negative, the other part has to be positive. And this is what he thought the plum pudding model must have looked like. I had some strange taste, I'll give you that. This is easier for, this is just an animated version. I like to think of this as a chocolate chip cookie model. See, if you think of it as a chocolate chip cookie model, the chips represent the little tiny bits of negative charge that made up that light that he was messing with. And the dough, well, you know, that would have been the positive part. And he could get those little tiny chips, or the electrons, to leave the atom if you just give him a shove, a push, you know, like the push that came from an electrical field, the electricity that he passed through that beam. Now, Thomson is forever known for this amazing discovery. However, this model was almost instantaneously, that's funny, instantaneously proved to be wrong. That brings us to the discovery of the proton and much, much more by this guy. I mean, wow. Ernest Rutherford. Now, he was trying to support Thomson's ideas. He was trying, like, hey, buddy, I got your back on this. We'll show the world who's laughing at you that you're absolutely right. And he worked a lot with radioactive stuff. In fact, if you, like, take a Geiger counter to his labs in England today at the Cavendish Laboratory, it still gives off radiation. Yeah, the dude really liked to play with radioactive stuff. Anyway, there he is with his famous gold foil experiment, and he did win a Nobel Peace for his work. And here is the experiment, the ever famous gold foil experiment. Well, what he did, and, you know, this thing is amazing. So anyway, what he did is he shot alpha particles. Now, alpha particles are positively charged particles. These little alpha particles here, they are positively charged particles, and they flow in a straight line. I can't really see these particles. It's radiation. It's invisible. But what he did is when that passed through this extremely thin piece of gold foil, I have no idea how he cut it that small, but he fully expected if Thomson had been correct, they would all have gone right there. And oh my gosh, they didn't. Some of them ricocheted here and here and here and way back here. Which made him wonder, wonder what's going on. Yeah, I mean, I would have gone, wow, that's cool. But Rutherford's like, whoa, what's going on here? So this is kind of what he figured was happening. He said the atom was, and this part was like amazing, mostly empty space. Yeah, because see, these alpha particles were going straight through some of the time, like this one, but sometimes they would get like ricocheted back. And what he figured is that on these times that they were these positively charged alpha particles were deflecting, was that they passed very close to a very tiny but positively charged nucleus. And he thought, well, if the positive nucleus was here, the electrons must be around here somewhere, and so small that they have no effect on the alpha particles at all. So he came up with the idea of mostly empty space and a positively charged nucleus that was really, 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 really small. And for this discovery, we will always know Rutherford as the man with the gold foil, and a really bad model of the atom, because we now know his model, while better than the others, still wasn't right. But what he did get right was the mostly empty space and a positively charged nucleus.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Now, I could keep talking about how we eventually get to quantum mechanics, but for our purposes, this is where I'm going to leave you hanging on Rutherford's bad atom. It gets better, it really does. But to review, Dalton, he said atoms were small, little spherical balls, indivisible. Can't break them apart. And Thomson came along and went, no, the atom looks more like a chocolate chip cookie. Well, plum pudding. But anyway, and it's made up of positives and it's made up of negatives. And if you give the negatives a push, you can get the negative charges to come off the atom. And while Thomson's model wasn't bad, Rutherford came along and said, we're going to blow a big hole in that model. And what really is happening is the atom is mostly empty space with a positively charged nucleus, and the electrons are out there somewhere. And on that happy note, the next video is going to deal with the parts of the atom.